Assalamualaikum and greetings everyone, and thank you for being here. We are from Group 7 and today we will be presenting on the topic AC circuit analysis in HVAC systems. My name is Ilham Salihin bin Mawasari and these are my group members. Our presentation focuses on how alternating current or AC is used and analyzed in HVAC systems, which stands for heating, ventilation, and air conditioning. In our presentation, we first explain the basic theory behind AC sinusoidal analysis, followed by in real-world application in HVAC systems. Then we show our analysis results, discuss findings, and finally conclude some recommendations to improve energy efficiency. For the introduction, what is AC sinusoidal meaning and why is the importance in HVAC systems? AC sinusoidal analysis allows us to study how alternating currents vary over time and how they influence power delivery in HVAC units. Understanding these characteristics helps improve energy efficiency and equipment reliability. Its theory. There are 4 theories in AC sinusoidal. The first one is phasors. Second, impedance. Third, power in AC circuit. And the last one is frequency response. So, what is phasors? And what is it for? Phasors are rotating vectors used in AC circuits to simplify the analysis of sinusoidal voltages and currents. They represent both the amplitude, length, and phase angles, which is directions of sinusoid, allowing complex AC circuits to be analyzed using algebra rather than calculus. If you look on the right, this is one of the examples of phasor diagram. The second one is impedance. What is it and what is it for? Impedance is the total opposition to alternating current AC flow in an electrical circuit combining both resistance and reactance. Impedance is a crucial concept for analyzing AC circuit where frequency is a major factor. If you look on the right diagram or the right picture, these are the formula for the impedance. The next one is power in AC circuit. And what is it and what is it for? In AC circuit, power is categorized into average power P, average for S, and reactive power. Power is an AC circuit is often calculated using the root mean square RMS values for voltage and current multiplied by the power factor. The instantaneous power fluctuates over time, but the average power is still useful power consumed by the circuit's resistance. If you look on the right, these are the formulas for the power in AC circuit. And the last one is frequency response. What is it and what is it for? Frequency response is an AC circuit is to study how the circuit's behavior, specifically its output magnitude and phase changes. The input frequency varies. It measures of a circuit's gain or loss at a different frequency, which is crucial for understanding and designing systems like filters, amplifiers, and communication circuits. Frequency response is typically represented by plotting the magnitude and phase shift against a range of frequencies. If you look on the right picture or examples, these are the examples of frequency response. There are resistor AC response, capacitor AC response, inductor AC response, and RCR series AC response.
Now, let's apply all the theory we have discussed to something more practical, the HVAC system itself. In general, HVAC units are powered by AC, alternating current. Smaller systems such as one we have at home usually use a single phase AC, while larger commercial system use a 3-phase AC. Inside every air conditioning unit, there are 2 main electrical components. The compressor motor, which is basically the head of air conditioning system, and it compresses the refrigerant, allowing heat to be transferred efficiently. And another one, the fan motor, which circulates the air either through the cooling coil or heating element to maintain indoor temperature. Now, both of these components are inductive load because they use inductive motor. Inductive load have coil or windings that store energy in a magnetic field, and this causes the current to lag behind the voltage. Basically, when the current lags, it creates what we call lagging power factor, which reduce efficiency lah. This happens because part of the current is not used for useful work. It is used to build magnetic field instead. So even though the system draw electrical power, not all of it's converted into the mechanical work or cooling. That's why the power factor become less than 1, and the system use more current than necessary. To solve this, we can add a capacitor to the circuit. These are the device that store electrical energy in the electrical field. The capacitor can generate a leading current, which is the opposite of lagging current produced by inductor. When both are combined, the leading and the lagging current cancel each other out. So balance the phase difference between voltage and current, improving the power factor, reducing waste energy, and making the HVAC system run more efficiently. So next, let's see a real world case study. So here the key part: without a capacitor, the inductive reactance cause the current to lag far behind the voltage, resulting in a low power factor. This means more current is drawn from supply and delivers same amount of the real power, which lead of energy losses, voltage drop, and heating in the wires. But when the run capacitor is added, it generates leading current that partially cancel the lagging current. This current improves the power factor, allowing the same motor to run more efficiently while drawing less current. So overall, the capacitor acts as a power factor corrector. It helps reduce the total current, it decreases the energy losses, and it's allowed the HVAC system to deliver the same cooling output while using less power from the supply. I think let's continue to the next one.
Alright, now let's move on to the analysis part of this topic. In this section, we studied a single phase AC circuit that represents an HVAC motor load. The circuit used a 240 volt 50 Hz AC source, which is similar to the normal household supply in Malaysia. This source is connected to what we call an RL load. That means it has both resistance and inductance. The resistor limits the current while the inductor causes the current to lag behind the voltage, just like what happened in an electric motor. For this example, we use a resistance of 30 ohms and an inductance of 0.1 Henry. To understand how the circuit behaves, we did a few calculations. First, we calculate the inductive reactance written as X sub L equal to pi FL. When we put the number in, 2 times pi times 50 times 0.1, we get 31.4 ohms. Next, step 2, we found the impedance Z equal the square root of R squared plus X sub L squared. That the square root of 30 required plus 31.4 square, which equal 43.1 ohms. Then we calculate the current using I equals V divided by Z. The 240 divided by 43.1 giving us 5.6 ampere. Step 4, we found the power factor using cosine pi equal R divided by Z. So 30 divided by 43.1 equals 0.696 or only 0.7. This means the circuit has a lagging power factor, which is normal for inductive load like motors and transformers. To make the circuit more efficient, we can add a capacitor in parallel with the load. The capacitor gives a leading current that helps cancel out part of the lagging current from the inductor. This process is called power factor correction. We can find the value of the required capacitor using this formula. C equal the difference between Q sub L and Q sub T divided by V squared times omega. Here Q sub L is the reactive power before correction, and Q sub T is the target reactive power of correction after correction. By choosing the right capacitor, the power factor moves closer to 1, which means less current is drawn and the system becomes more efficient. For conclusion, AC analysis is essential for understanding HVAC electrical performance. Compressor and fan motors behave as inductive load, lowering the power factor correction, improve efficiency, and reduce energy loss. Proper impedance and phase angle analysis enhance system reliability. Using VFDs and capacitor banks can optimize overall HVAC energy performance. So overall, this analysis helps us understand how inductive load affect power and how adding a capacitor can improve the system efficiency by correcting the power factor. That's all from us. Thank you.